This is my RGB time fountain version 2. It's an improved version of my original design you can see here. In this video, I'll be showing you my design and build process. Filming this project was really difficult because I don't have a good camera yet, and the time fountain is made out of reflective black, whilst also having strobe lights, so it really messes with the camera. The effect actually looks even better in person. This video is sponsored by JLC PCB, who also provided the PCBs for this project. The main improvements to the design are the enclosure and improved circuit. The enclosure design needed to be somewhat similar to my original design, but slimmed down, easier to make and solve a few issues. The original design was wooden, which wasn't ideal, as it would absorb water and didn't show the drops against the wooden back very well. This is why I ended up adding black vinyl inside of the fountain. To solve both of these issues, I decided to use black acrylic for my version 2. It doesn't absorb water, shows the drops nicely, and can easily be laser cut. The pump still needs to be at the top of the fountain, so it would produce consistent drops when combined with the nozzle. And I wanted the electronics to be located there as well, so it's less likely they would get wet, short circuit or corrode. The reservoir still needed to be at the bottom of the fountain to collect the water and feed the pump. The levitating effect relies on having a stream of water drops that are lit by precisely timed strobe lights. This means that the circuit needs to have appropriate components to control a pump and LEDs. When designing a circuit, I normally break it down into smaller sections, or different functions. In this case, I needed RGB LED strips of the strobe lights, Bluetooth communication to control the various parameters, a 12-volt diaphragm pump to produce the water drops, and a way to keep the drop rate constant, as it can drift over time. There are many possible solutions and components that could have been used, but I chose these ones because they're relatively cheap, common, easy to use, and most importantly, work for the project. The diaphragm pump is rated for 12 volts, which is convenient because the LED strips are too, and the Arduino Nano can be powered by a 12 volt supply via the V-in pin. The Arduino's onboard voltage regulator will limit it to 5 volts, which can then be used to power the other components too. So all that is needed to power the circuit is a 12 volt input. To switch the LEDs and pump on and off, I chose to use some IRL-Z44N logic level MOSFETs. They can be switched fully on by a 5 volt signal from the Arduino and control a much higher voltage and current. I used a JDY31 Bluetooth serial pass-through module to allow wireless communications with the Arduino. I believe it's replaced all the HC05 and 06 Bluetooth modules, but they share the same pin out, so I'll also work with my time fountain. The Bluetooth module's RX pin requires 3.3 volts, not 5 volts, so a potential divider is required to lower the voltage from the Arduino's TX pin and prevent any damage to the module. I did some calculations and chose 15k and 33k resistors, which gives a voltage of about 3.4 volts, which will be perfectly acceptable. As I previously mentioned, the rate of the drops has a tendency to drift slightly, so I wanted to implement a PID controller on the pump to make sure it stays consistent. The pump's motor doesn't have an encoder, or space to add one, so the easiest solution I could think of was to measure the water drops themselves using an infrared diode and receiver. I didn't want the Arduino to have to measure and calculate the control loop for the pump, as this would change the execution time for the strobe code and leave artifacts that would detract from the effect. This meant I would need a slave microcontroller to deal with the pump's control loop. I had some ATtiny85s to hand, and these would be perfect for the application because they have enough GPIO pins to read the IR diodes, PWM the pump's MOSFET, and communicate with the Arduino via I2C. The internal pull-up resistors on the Arduino aren't ideal for I2C because they have a high resistance, so I added some 4.7k pull-up resistors to the I2C bus. If you look at the schematic, you can see a healthy sprinkling of capacitors around. The one on pin PB4 of the ATtiny85 is to smooth the signal from the IR receiver so it gets an accurate count of the water drops. The other capacitors are to reduce any voltage drops when switching the LEDs and pump, and to suppress the electrical noise from the pump. A flyback diode is also used to eliminate any voltage spikes from the switching of the pump's motor on and off due to the PWM signal. Once I had an idea of all the components I would need, I made a quick sketch of the schematic, then began prototyping it on breadboards to test it would all work and I hadn't made any stupid mistakes. After I tested it, I removed all the stupid mistakes and tested it again. This time I removed all less stupid mistakes and it worked. The next steps were to design the schematic and then the actual PCB. A friend recommended using EasyEDA, which I did. It was fairly easy to learn to use, has a massive library of components and even user-created ones to use, which saved a lot of time. Once I'd finished the schematic, I clicked Convert to PCB, which then gives you all the component footprints and shows the required connections you need to make. After I'd arranged all the components and drew the tracks how I wanted, I ended up with the PCB you can see here. I performed a design rule check, which helps find mistakes in the PCB design such as missing connections or tracks that are too close together. The The DRC was successful and there weren't any errors, so I generated the Gerber files and saved them. Next, I went to jlcpcb.com, link in the description, to get the PCBs manufactured. I clicked the Get Quote button and uploaded my Gerber files. Once they were processed, a preview was displayed of the front and back. I had a quick look to check that the PCB I uploaded was the right one, and also checked the other settings were what I wanted. I was happy with everything, so I saved it to my cart and checked out. I'm very excited to see my boards now they've arrived in the post, as they're the first PCBs I've designed since university. It looks like they've sent a cute little keyring with the boards as well. All the boards look great, and I can't see any defects in them, so let's hope I didn't make any mistakes and they work. I thought it'd be interesting to take a closer look at them under my microscope, and also a good excuse to use my Delta Robot for something. So here I have my Delta Robot holding and adjusting the position of my USB microscope above my PCB. The microscope's view is in the top left, but for some unknown reason I forgot to get the footage of both the microscope and Delta Robot at the same time, so the movements don't match up. This footage is still taken by the microscope while mounted on the Delta Robot though. You can see the image wobbles and looks like jelly after removement because of the small vibrations in the Delta Robot, but that only lasts for a few seconds before settling down. I'm very happy with the boards. All the tracks and solder pads look really clean and consistent, so now on to soldering all the components to the PCB. I picked out the components I needed and laid them out in my components tray. I find it helps to have all the components out in view so I can decide on the best order to solder them. Normally it's easiest to attach the parts to the lowest profile first and move up in size as you go. Trying to film my soldering actually makes it much more difficult because I have to make sure I don't block the camera or move the parts too much, so end up having to solder in awkward positions. I have my soldering iron set to 350 degrees, centigrade that is, not Kelvin, and I use a 0.6mm diameter 6337 tin lead solder with 2% flux core. You can use anything you want, but this just worked well for me. Now when soldering, I normally have a little fan on my desk to blow the fumes away, so they're not constantly going in my face and being inhaled. One slight difficulty I did have with the boards was soldering the ground connections. I had them all connected together by the ground plane, which acts as a massive heatsink and makes it much more difficult for the solder to melt and flow well. They do make good connections, but require the soldering iron to be held on them for longer to heat up enough to let the solder flow. The capacitor values and placements came from a lot of testing and probing with my oscilloscope and my experience of electronics. It still took quite a while to get the electrical noise down to a level I was happy with, but I think it was worth the effort to create a circuit that works consistently. I like the microcontrollers I use in projects to be removable, so they can easily be reprogrammed or replaced if I accidentally fry one, which is why I use headers and dip socket for the Arduino and ATtiny respectively, instead of soldering them directly into the PCB. To ensure the two rows of headers for the Arduino line up, I actually put the male headers and Arduino in place to hold them in parallel while I soldered the first few pins. Although I don't show it much, I use helping hands a ton to hold the components and PCB in place while soldering. That's now all the components soldered to the PCB. All I need to do now is solder the wires to the LED strips, DC barrel jack and pump. They attach to the circuit via 4-pin connectors and screw terminals rather than soldering them directly to it, because it makes assembling the time fountain much easier. The effect works better with brighter strobe lights, so the LED strips I chose this time have twice as many LEDs per meter than the ones I used in the previous version. One minor issue I came across was the order of the LED strips. As you can see printed on them from the top down, is plus 12 volts, then BRG, which is the same order I used on my PCB design. However, I discovered that the blue and green channels are switched. Luckily this is a really simple issue to fix in code by swapping what the blue and green pins are defined as. I cut the LED strip into 4 45cm lengths. The waterproof coating over the solder pads on one end needed to be removed so that I could attach the wires. Because there will be 2 strips each side, I soldered the 2 pairs in parallel so that I would only have one connector per side going to the PCB. I always cut a little bit of the LED strip backing off where the heat shrink will go, otherwise it gets trapped under the heat shrink and becomes very difficult to peel off. To help reduce the electrical noise from the motor, I soldered a 0.1 microfarad capacitor across the terminals. I modelled the parts in Autodesk Inventor, then created an assembly of the time fountain to check all the parts would fit together correctly and would actually be possible to assemble using the appropriate tools. I exported the parts that would be 3D printed to STL files, so they could be imported into Slicer for 3D printing. All but 2 of the parts were designed to be printed without supports, so it's important to arrange everything in the correct orientation. I checked the layers all looked good, then exported the G-code to my SD card. I used my ANET A8 3D printer for all of the parts. They were printed in black PLA with a 0.4mm nozzle, a layer height of 0.23mm and 20% infill. These parts are mostly brackets and on the inside of the time fountain, so won't be seen and don't need a super high resolution. Here are the 3D printed parts. They all came out pretty well, but I'm still going to do a little bit of cleanup on them to make sure everything fits together really well and there aren't any small gaps when everything is bolted together. Originally I designed the brackets without hexagonal holes to hold the nylock nuts. I later realised that being able to press fit the nuts into hexagonal holes would make the assembly a million times easier. On a couple of the more awkward parts to bolt together, I had the nut be pushed out of its hole when I tried to screw in the bolt. To stop it from happening again, I glued the nuts in place. In the past I've designed things that can't be put together because there isn't room to get an Allen key or spanner in to tighten the nuts and bolts, so that's a mistake I try to avoid now. The panels for the enclosure are all designed to be laser cut out of 5mm thick acrylic. To ensure they all fitted well together, I had to take into account the kerf of the laser when modelling them. The kerf is the width of material the laser burns away due to the width of the beam. It's normally around 0.1mm either side of the cut lines for a CO2 laser. I exported the faces of the parts, then arranged them in a laser cutting services template using Inkscape. I sent the files off and received the laser cut acrylic in the post. You may not notice, but I've subtly edited and sped up parts of the build process to make it more interesting to watch, so don't worry if assembling it takes you a little longer than I show here. Assembling the enclosure is fairly simple and just requires an Allen key and a lot of screwing. Although the 5mm thick acrylic is fairly strong, it can still crack, so I would advise not over tightening the bolts. This is where I noticed I made my first mistake. I forgot to put the foot on before bolting it together, which means I have to undo the bolt and screw it back in, but this time with the foot. Because of the added thickness of the feet, I used 14mm bolts here instead of the 12mm ones, which are used for all the other brackets. You can see at this point, I realise I've bolted the brackets on the wrong side of the side panel, hence why it doesn't fit. After some unbolting and putting the brackets on the right side, it fits on. If you watch carefully here, you can see I don't forget to bolt on the feet this time. Next, I finish bolting the top to the side panel, then move on to attaching the front panel. That's now the enclosure assembled. The back panel isn't bolted on, but instead held in place by 3D printed pegs, so it can easily be removed, as you will see later. I've just done a quick test fit to make sure everything will fit how expected, and that the wires and tubing will be long enough. It all seems good, so I'm going to stick everything down and bolt it in. The pump mount consists of 4 parts, 2 semicircular brackets that clamp around the pump, and 2 arms that connect the brackets to the enclosure, suspending the pump in place. I have slightly changed the design to reduce the vibrations from the pump since filming this. I added a rubber ring that goes around the pump, which the brackets now clamp onto, but I'll be covering the soundproofing improvements in another video. It's important to note that the pump intake and outlet nozzles aren't centred, so they need to go in the correct way around for the tubing to fit and everything else to line up properly. Here I'm threading the wires of the DC power socket that I soldered up earlier through its mounting bracket. The power socket then press fits into the hole. Next, the nut for the power socket gets threaded over the wires and tightened onto the socket, preventing it from being pulled back out. When doing this part, I realised it would have been far simpler to have mounted the power socket in the 3D printed bracket before I bolted it to the acrylic enclosure. The wires can now be threaded through the corner bracket with the loop, then up between the inner panel's corner cutouts and up into the top section of the time fountain. The LED strips fit through slots in the sides of the inner panels. They need to be inserted from the top section down because the connectors, solder joints and heat shrink on the ends of them won't fit through the slots easily. I made sure the strips were lined up before peeling off the backing and sticking them down. I then repeated this for the strips on the opposite side. I designed the LEDs to be either side of the stream of water drops so that they would illuminate them well, giving a strong effect, and so that the LEDs wouldn't be visible when looking straight on at the fountain. Here I'm using my heat gun to warm up the tubing so it will stretch over the pump inlet more easily, and so I can put some bends in it to make it easier to install later. The tubing gets threaded through the same holes as the wires from the power socket, but has to be inserted from the top down because the stretched end of the pump's nozzle won't fit through the cutouts in the panels. Before I rotate the pump into place and connect the tubing, I want to attach everything to the PCB while I still have space to work with. I start with screwing the pump's wires into the terminal block, then the LED strip connectors and IR diodes from the nozzle, and finally I attach the wires from the power socket before placing the PCB at the back of the enclosure. The pump can now have the tubing fitted and be pushed back into place. While pushing the pump back, I have to pull the excess tubing further down through the enclosure. Here I'm putting on the short bit of tubing that's used as the nozzle and the IR diode holding section around it. Mounting the bottom funnel and attaching the tubing to the intake restriction clamp is probably the part of the assembly I struggled most with. The funnel slots into the acrylic panel, then rotates 90 degrees and locks in place, which is the easy part. The difficult part is fitting the tubing between the intake restriction clamp and funnel, and then inserting the second bolt. The nylock nuts kept falling out when I tried to screw in the bolts, so they are some of the ones I glued in place. I also had to use a longer 20mm bolt for the clamp so they'd be easier to install. After a lot of struggling off camera, I managed to get it all in place. Obviously the tubing is a bit long, so I just cut it down to the right length which will allow it to reach the bottom of the reservoir. The last things to do before testing are to add some stainless steel scourer to the funnel to reduce the splashing and noise, put the reservoir container in and fill it with water. You can see I had to add way more of the stainless steel scourer to stop the splashing. This obviously looks terrible, so I had to find a better solution. While doing some research, I came across a video showing what they called magic water. It uses a vertical spike to dissipate the water drops quietly without splashing, so I tested the idea. I designed and 3D printed several iterations of what I called an anti-splash spike, until I got the design that you see here that worked perfectly. So I'm going to put the back panel back on and show some proper demos of it working. I'm really happy with how my RGB time fountain has turned out. I've put a ton of work into it and I think it's paid off. However, there's still a lot more development I want to do. I have ideas for new nozzle designs, new effects to add, and some code improvements. I wanted to cover so much in this video, but I had to cut it down to just the design and build process because it was getting way too long. So I'm making another video to show the soundproofing I added, some testing and comparisons of parts, and explain how the effects work and the algorithms I use to achieve them. If there's anything you want me to explain in the video, leave a comment and I'll try to include it. I'm releasing the parts list, all the design files, and code for anyone who's interested. Links will be in the description. I will now leave you with a little sneak peek at a double drop nozzle I'm developing. Hopefully I'll have some other interesting nozzle designs to show you in a future video too. If you enjoyed the video, please leave a like, and if you're interested in the work I'm doing, consider subscribing for more. I want to try and improve the quality of my videos, so if there's anything I can do better, let me know in the comments down below.